SwayamPrabha. Digital India. Educated India.
Good morning students, welcome to the NPTEL lecture on architectural acoustics. This is the third lecture where we will discuss the frequency and the octave. If you remember, in the lecture number 2 we have discussed about the general propagation of the sound in a media like air or in any other kind of media. And we have actually thought of some kind of the parameters, and we have actually given some kind of a relations to one parameter to the other. We also found out the what should be the appropriate propagation equations also. So, there we have discussed one typical parameter of the sound as a frequency, and this frequency plays a major role in building acoustics or any kind of the acoustical phenomena. So, in this lecture there are two learning objectives. So, if there are various combinations of the frequencies, how to differentiate or the distinguish between them, that is the first objective of this lecture. And second objective is to interpret the superimposition of the wave motion. That is also going to be happen because of the if sound cannot be a single frequency sound, it is actually the mixed frequency sound. So, how the sound will superimpose with the other, and that kind of a scenario we have to see. So, the frequency, as we already discussed in the lecture number 2, is that it is a number of oscillations of the cycles that is going to be dispatched in a unit time in a wave motion, and the unit is hertz or CPS. And out of the hundreds or out of the thousands of the frequencies available in the nature, the human being can only respond to 20 to 20,000 hertz frequency. Now, this spectrum is also very huge spectrum of the frequency we can actually map in our brain. Now, let us discuss about this frequency, how this frequency has created this kind of a sensation, and that is called as a tone. A sensation, sound sensation because of some kind of a frequency is called tone. There are two type of tone. The one is called the pure tone. The pure tone is a single frequency sound, only a particular frequency, nothing else. A striking of some kind of a vibrating object like a tuning fork or maybe some kind of a guitar string is a pure tone. It involve only one frequency. There is the second type of tone is called the complex tone, where there are two or more than two number of frequency mixed together. So, that is a speech, that speech I am giving to you, or maybe some kind of a music, any kind of noise in roadside, and practically in nature 99% of the sound is a complex tone or the mixed frequency sound. So, when this mixed frequency goes into that, so we will have some kind of superimposition. So, superimposition will go to in a way that a sound wave is having, suppose, a simple motion like this, which can be talked as, suppose this is the first sound wave, that is why I am writing y 1 is suppose some amplitude 1 sin omega 1 t, or this can be written as a 1 sin 2 pi f t. This is another frequency, suppose something like this, which can be written in like this, a 2 sin 2 pi f 2 t, where your this f 2 and f 1 are the two different frequencies. Now, at a particular time t, this both the frequency, if you add, when both the frequencies actually merge together, you will get a different type of frequency, and this two superimposition in a particular time t gives you some different type of the addition of this y 1 plus y 2 will be equal to your a 1 sin 2 pi f 1 t plus a 2 sin f 2 t. And because of the variation of this a 1 and a 2, because of the variation of your f 1 and f 2, you will get different type of frequency and different type of the amplitude in nature. So, it is only 2, there may be 3, there may be 4, and if it is much more, the things will be very much complicated. So, let us take a complex tone. In the complex tone is a mixed frequencies. So, I have taken a series of complex series of frequency which gives me a complex tone. It starts from 50, then 75, like that. So, in this I have identified a first frequency, the minimum one, the lowest one out of this particular bracket, and this minimum one in a particular complex tone, that minimum frequency or the lowest frequency is called the fundamental tone, and the rest frequency which is the higher than this particular fundamental tone are called overtone or the integral frequencies or the partials. There are a lot of names, overtones probably the best fitted kind of a thing. Now, in that overtone, if I see there is a good relation with the fundamental frequency, there are some frequency may exist in this overtone which may have a very good relation with the fundamental tone. Suppose this red color ones, the 50 is the fundamental tone. You see this 100, there is 250 also, there is a 450 also, and there is a 750 also. They are the numerical multipliers of the fundamental tones. So, 2 multiplied by 50 is your 100, something like the 9 multiplied of 50 is your the 450. So, those red color frequencies in that complex tone is called the harmonics. So, harmonics is a part of the partials or the part of the overtone. So, I may say that all harmonics are overtones, but all overtones are not harmonic. Then let us take this particular band of the spectrum of the complex tone, where this 25 is your the fundamental tone, and it has lot of I mean in fact it is a series of, it is a harmonic. So, it is all are harmonic, every frequency is the multiplier, the integer multiplier of the first frequency, the lowest frequency or the fundamental frequency. But again there is a good relation exists between them. If you take 25, if you take 100, if you take 200, 400 and 800, they are definitely harmonics, they are definitely multiplier, the integer multiplier, but they are double of other. I mean there is this one is also going to be double of other, and this is called octave. So, now let us go to the octave band central frequency. The problem with us is that we have lot of frequency to be handled from 20 to 20,000. So, out of that this 10 frequencies are identified which are a complete set of octave which covers the total set of audible frequency. It starts from 31.5, then double of that 31.5 is 63, then almost double of that is 125, and like that it goes up to 16,000. So, these 10 frequencies are called octave band, and this octave band has taken as the criteria for any kind of a testing or any kind of the statistical output to generate for any kind of a noise or any kind of a sound atmosphere to test or maybe making some kind of a benchmarking or so. So, here if I take the logarithmic of that particular octave frequency and multiply that by 10. So, it is 10 of log of that f is that frequency. So, something like 10 log 31.5 is almost going to be 15. Similarly, 10 log 63, the next one is 18. So, this particular 10 log the frequency that called band number. So, these are the band number for each those 10 octave band central frequency. And very interestingly, this band number is jumping by 3. First it starts with 15, then it is 18, 21, 24 like that, where the frequency actually going to be doubled with another. It is a GP series, but this is a arithmetic progression series. Now, this 31.5 or 63, whatever may be the frequency, let us say that frequency is f and it has two arms, one is lower arm and one is the upper arm. So, lower arm is f minus 0.3 times f or almost 0.7 f is the lower bandwidth limit, and the upper bandwidth limit or the upper arm is something like f plus 0.4 times f, which is 1.4 f. So, if I go to the 31.5 frequency, by virtue of this calculation I find 22 is the lower band limit of that band of 31.5 and 44 is the upper limit of the band of 31.5. Now, let us see the second one 63. So, similarly, if I put 63 and this f is now twice of f because it is in the octave. So, I will find this is 0.14 of f, these two are matches with each other, and this is 2.8 f. So, now if I multiply with 0.7 into this 63, which comes from this particular here, it is 44 and this is 88. So, the 44 and the 88 is the limit lower and upper limit of 63, 44 and 22 are the limit for 31.5. So, like that each will have its lower and upper limit, and once the frequency which is the earlier frequency, the upper limit will be the equal to the lower limit of the next higher frequency, and by virtue of that I can rewrite this particular band number, and the bandwidth like 22 and 44 is for 31.5, 44 and 88 is for 63, 88 and 175 is for 125 like that. So, all the spectrum and the octave band central frequency, that is OBCF, the band number and the bandwidth are ready for you. So, then if you see from the bandwidth or the frequency from the 22 frequency to 22,400, which is in our audible range, is covered by all those 10 OBCF. Now, what is the necessity of the octave band? The necessity of the octave band is very simple and straightforward. The first one, the octave band gives a logical set of some frequency out of many, because I have a problem. I have problem because I have frequencies from 20 to 20,000, which is audible by a human being. So, from that, if I want to select something, select some maybe 10, 15, I need a certain amount of logical understanding, and it gives me that. Number 2, the logarithm of the octave frequencies is separated by the equal distance, because I have seen that the logarithmic of 1 is separated by 3 to the next higher and the 3 to the next higher. So, while I will plot a graph in the in some to test some material or some kind of the environmental acoustics, I have only 10 such equal distribution line. If I have taken the all the 20 to 20,000, then the x axis of the particular frequency will be too high to handle. The third important thing is that the octave band central frequency provide a common platform for any kind of material testing and assess any kind of acoustical data. So, worldwide globally it has been taken as this octave band, that 31.5 to 16,000 are these 10 frequencies are set for any kind of acoustical testing and any kind of material data handling and all the kind of the noise and acoustical data purpose. Now, there is a 1/3 octave band. People are not very happy with this 10 frequency. Now, they go much more detailed, because there are a lot of parameters in the noise or maybe the sound transmission, which can be understood by these 10 frequencies, but we need maybe some more set of frequency to understand that particular phenomena better. So, that is why let us consider some other set of frequency and let us make that particular set larger, instead of 10 maybe more than that 20, 25, and how to generate that one, that is the very important and the logical way let us generate. So, as we know, this 31.5 is octave band and also the 63, whose band number is 15 and band number is 18. So, in between this 15 and 18 we have two more numbers, 17 and 16 and 17, and like that. So, let us write all those band numbers. So, fill the gap between the 15 and 18 by virtue of 16 and 17, and then do the anti-logarithmic of that and divided by 10 and anti-log of that, and then if you will get the another set of frequency. So, we will fill this particular the band number by 2 more digit and equally spaced, and anti-logarithmic of that will give you another set of frequency, and that frequency set is your octave band. I am sorry, the 1/3 octave band. This 1/3 octave band is filled by 2 more frequencies in between the octave frequency. So, see this 31.5 and 63, which are the octave, which is also called 1/1 octave band, is filled by another 2 frequency 40 and 50 in between and make it as a 1/3 octave band. So, each of those 10 will now produced like this. So, this is red colors on the 1/1 octave and these black colors are the 1/3 octave. So, as we know, the 1/1 octave is twice of other, 31.5 into 2 is your 63, but what is the relation between them? If you just divide 31.5 with 25, 40 with 31.5, will get almost like 1.66, 1.26, 1.25 like that. And if you see generally this 1/3 octave band is separated by the other with the cube root of 2, this particular factor, which is very near to 1.2599. So, here in this table we have this purple color the column, which is the octave, and there are the series of band number, the anti-log of that band number, and again this last column gives you the 1/3 octave, and this is the till that we can go till the 20,000 as the 1/3, the last one is the 1/3 octave. So, there are 30 such 1/3 octave band frequencies, starts from 25 to 20,000, and out of that we have 10 number of this red color one, which are the octave band, which is the 1 by 1 octave band. So, 10 octave band and 30 1/3 octave band. So, most of the cases for testing or any kind of a general purpose, we take 10 octave band, but sometimes we need to do the critical analysis, we need to do some kind of the conformatory kind of analysis for any kind of a material testing or any kind of acoustical surroundings to check whether it is perfect or not. Then we go to the this 1/3 octave band and the 30 such frequencies. And these 30 frequencies or the 10 frequencies are very much wide. Again it is very much wide. It starts from 25 to 20,000, and here it starts from 31.5 to 16,000. So, here the behavior of the sound also not perfectly synchronized with the all frequencies. So, here for that we have categorized the frequencies as a low, medium or the high frequency. So, as you see, this is 20 to the 16,000, where all the octave are separated by the equal distance, which is maybe the 3 by the logarithmic in by virtue of its logarithm. And if I draw two perpendicular line from 250 hertz and the 2000 hertz, this total spectrum is subdivided into 3 parts, and in these 3 parts, the first part, which is called the lower frequency, which is 20 to 250, the middle frequencies are 250 to 20,000, and the higher frequency is the 20,000 to that onward till the 20,000 or 22,000 to 20,000. And the human can listen 20,000 to 2,000 frequencies, as you know, and this spectrum is mainly have these 3 categories, which I have just now tell you, like the low, medium and the high frequency is also has a different name, bass. Bass is the low frequency range of sound, which is cover almost 20 to 250 hertz, which is very sound like a tabla or sound like some kind of a sound which is having some not a that much of intense pitch kind of the sensation. The middle frequencies are come within that 250 to 2000 hertz, which is very normal and which is very much widely used for any kind of the music or any kind of speech. The treble sound, which is called the high frequency sound, which is more than 20,000 hertz or so. Some part of the music and some part of the human voice also comes into that particular zone, the treble zone, or there are some kind of a machine, some kind of the equipment gives some kind of a treble sound, which is very high frequency zone. Next, let us discuss the frequency range of the audible sound and all. In audible sound also, in case of that also we have this the octave in separated by equal distance, and this audible sound is generally of something like this nature. The hearing range of the young person like you people are almost the full spectrum, but if you are old, somebody is old, so then the spectrum of the hearing will gradually shrink down, and it is maybe limited to the 4,000 frequencies or so. Now, let us discuss about the male and the female voice. Male voice starts from little bit of bass towards the 4,000 or so. Female voice is separated a bit. There the female voice is bit of the treble kind of a thing, where it is 250 to the 8,000 is the range of the female voice also. Music, next is the music. The musical instrument again take a very wide range. It is a bass music, which is in this zone till 250s or so. There are mid frequencies also, and there are very high frequencies also. So, by virtue of that, we can have differentiate frequency level, we can have different type of the quality of the music based on that particular thing. And let us go to the a Excel chart, and we will see how a superimposition can be done in a Excel chart. So, let us open this one. So, I have 3 frequencies can be mapped over here. So, in the first frequency, if I say suppose this is some frequency like 25, and it gives me the frequency 25 in pink color, and the second one suppose I give some frequency like suppose 69. So, it gives some frequency like 69, this is in green color, second one, and the third one, and this two, the first frequency 69 and the second frequency 25 is superimposed suppose, and you will find out this this one is the superimposed sign frequency of the sound or the propagation of the sound. Let us take the third frequency as some little higher frequency, suppose 1200, and then you will get the blue lines which is 1300, this one, and if you add this and this 3 wave front, you will get a very complex kind of a thing. So, this is your complex frequency or the complex tone, and this is your one tone pure tone, this is another pure tone, this is another pure tone. So, if those pure tones are in a some order, suppose this is 25. So, suppose I made it like 50, and if this is I made it like 75. So, you will get some kind of the rhythmic action, rhythmic kind of a thing in the harmonics. So, they are in harmonics, so they will get some kind of a rhythmic harmonic. So, as and when you are the frequencies in a complex tone are more in harmonics, you will find the music or this particular the sound is very interesting in character. There are some ups and downs. Let us see if I have something in octave. So, suppose this is 200. So, the next in case of octave it is twice of that, and this is 800, and you see it also gives you some kind of a beat, some high and low kind of the propagation on those kind of a thing. So, we understand that how a tone and the three such tones, pure tones can be made into a complex tone in this by addition of this frequencies and in the equation, the frequency equation. So, again let us go to the PowerPoint slide and come to the last slide, and as again it says kind of a homework kind of a thing. So, the thing is that can you distinguish the harmonics and octave from a given kind of a complex tone. Let us suppose if I give you a kind of a set frequencies like 23, 36 and all, can you find out the octave and the harmonics out of that complex tone? It is very simple. The next one probably you can just calculate, calculate in a piece of paper. Suppose there are two different sound wave I have given to you. The sound wave one is having an amplitude of 50 mm and the frequency of 79.577 hertz, and the second wave is having a lower amplitude, but higher frequency. 318.31 hertz is the frequency. So, they are two typical fundamental or the typical two pure tone. Now, can you superimpose them and can you find out what could be the particle displacement, the value of the y, that is y 1 plus y 2. Y 1 comes from the sound wave and y 2 comes from the sound wave 2, and can you find out the what should be the that y 1 plus y 2, that is the particle displacement after a time interval of 0.25. Try it, and if you have any problem you can contact for that, but try it by your own. And in the next lecture we will go to the we will go to the sound pressure level and the sound intensity level, which is going to create a kind of the initial benchmark scenario for understanding the reverberation time and all other sound physics level, which is very important in the building acoustics. So, thank you very much.